All right, guys. So, today we are going to analyze whether or not we successfully made aspirin last week, which is the goal, yeah? So, you know, as your textbook says, there's something like 10 million known organic compounds, okay? And most organic compounds are, you know, clear oils, yellow oils, white powders. I mean, that's, you know, that's most of them. White powders, maybe yellow powders, white to yellowish oils or powders, okay? So most of the time you're not going to be able to, you know, you're not going to be able to just look at the material and decide, like, okay, did we successfully make what we thought we made? So you're going to need to do some further analysis. And so there's a few different techniques that we're going to use today. And the first one I want to talk about is infrared spectroscopy. So you know that there is, hopefully at some point you've heard of the concept of electromagnetic radiation, right? And it's, you know, it covers a whole bunch of different phenomena that until you have a science class, perhaps you have no idea that they're related. Radio waves, visible light, X-rays, gamma rays, all these things. They are all the same thing. They are all electromagnetic radiation, just at different wavelengths, right? So electromagnetic radiation is a propagating wave. Okay. And to talk about the different parameters of electromagnetic radiation, it's good to have one fixed point in space. Okay, so we'll just fixed point. Okay. So, like any wave, it has a wavelength. Okay, and a lot of the time we'll define that. The distance between the two peaks. I did a terrible job on drawing. They should be the same height and everything, but the distance between the two peaks. Okay, lambda. All right. That's it. That's how we tend to define it. But it could also be the distance between the two troughs, the two bottom of the trough. It could actually be the distance between any two fixed points, as long as they were this analogous points on different locations, yeah? So, you know, the distance here is going to be the same, yeah? As that there. Okay, and then, so that's wavelength, and then frequency is if you, again, decide on a certain point of the wave, let's say the peak again, okay? With what frequency does it take to go through one cycle? One cycle would be one peak to one peak. That's one cycle. Okay? Or one trough to one trough. Okay? Again, it's arbitrary what you pick. Probably simplest just to think about it in terms of the troughs or the peaks or whatever. But how many times does one cycle, going peak to peak, go through a fixed point? That's frequency. Okay? And those are the two most basic ways of characterizing electromagnetic radiation. Okay? And so, really the only difference between gamma rays and infrared, visible light, radio waves, all these different wave types, is the wavelength. Okay? All right. The relationship, by the way, between frequency and wavelength is a very simple, elegant one. Okay. So this again is wavelength. That's frequency. and this is the speed of light. Okay. Right, and then, oh yeah, and then the energy of, and so, you know, there's that sort of complicated, mind-bending idea that wave is both, light is both a wave, but it's also a particle, right? It comes in packets called photons, okay? And photons can have different energies according to what wavelength they are. And so the energy of one photon was Planck's constant times the wavelength, okay? And we're not going to do, you know, not like Jen, we're not going to do a bunch of calculations with these things, but just try to refresh your memory on the general idea of electromagnetic radiation. Okay. All right. Yeah. And so I don't even think I'm going to bother to put up the spectrum. You know, you can put up the spectrum and start from, well, why not? I changed my mind. Have a really hard time reading. Here are my glasses. Oh, so gamma rays. Okay. And then this is wavelength. Okay. In meters. Okay. And so first there's gamma, and then comes X-rays. Okay. So this is going to go from smallest wavelengths and increasing. Okay. And so what is the energy doing? Maybe easier to think about what's the frequency doing. If wavelength is getting bigger, what's frequency doing? It's getting smaller. Yeah. Okay. And the energy is getting bigger. Okay. So wavelength and frequency are inversely related, and frequency and energy are directly related. Frequency goes up, energy goes up. Okay. All right. So X-rays. UV, this little area here, visible. And then we have IR, which is going to be important for us today. Radar. FM radio, and then something, I don't even know if it exists anyplace anymore. And then is broadcast television. It's broadcast through TV waves rather than cable. Okay, and so just to give you a rough idea of what those wavelengths look like, this is 10 to the negative 14. I just can't read these guys, I'm sorry. Shoot. Yeah, okay. I'll send them out to you. Yeah, sorry, I guess I shrunk this picture down from last time. So even with my reading glasses, I cannot read it. But in any case, you get an idea of the overall trend. Okay? Now, organic molecules will react in different ways to different wavelengths of light. Okay, so in the UV spectrum, it happens that if your molecule has alternating double bonds, okay? Remember we talked about alternating double bonds when we were talking about benzene last week, yeah? If if your molecule has alternating double bonds, it will absorb UV light. Okay? If it doesn't have alternating bonds, it doesn't tend to absorb UV light very well. Okay? Yeah. I mean, there are certain wavelengths of light, certain compounds that fluoresce, where if you take in, it will absorb one wavelength of light and actually promote an electron to a higher energy level. Okay? And then it will, the electron will fall back down to a different energy level and give off a different wavelength of light. That's what fluorescence, the basis of fluorescence is. Okay? And it turns out that with infrared light, okay, that it will absorb, okay, if the wavelength of light corresponds to the vibrating of bonds, okay, vibrating bonds. In Gen Chem, they may have mentioned it or maybe didn't, but bonds actually vibrate, okay? They go back and forth like that unless you're at absolute zero, okay? Even in solids, the bonds are vibrating, okay? And if you get the wavelength of light that corresponds to that frequency of vibration, the molecule will absorb that light, okay? All right, and this this property mirrors an idea in physics, which you may or may not have seen, and that's two weights connected by a spring, okay? And you may remember that the stronger the spring is, the higher the frequency. And that intuitively makes sense, right? If you have two weights connected by a spring, pull them apart, and it's a really strong spring, well, they're gonna, okay? And then a little bit of oversimplification, but the lower the mass of those weights on the spring, also the higher the frequency, okay? And you can see those same two trends in what type of bonds vibrate at what type of frequencies, okay? So I think probably in Dr. Organ's class already, you have an idea that bonds differ in strength, okay? Double bonds are stronger than single bonds, right? Triple bonds are even stronger than double bonds, okay? There's subtle differences in hybridization, right? If you make a bond with an sp3 orbital versus an sp2 orbital, the sp3 is a little bit stronger, okay? Backwards. sp2. The more s character you have, okay, the stronger the bond. All right. So an sp2. If everything else is the same, if you have a carbon that's bound to a hydrogen and it's sp2, that bond will be stronger than a carbon that's bonded to a hydrogen and it's using an sp3 orbital, okay, because of the hybridization. All right. Okay, so let's remind ourselves a little bit just of the formula of two vibrating springs. Okay. So for vibrating springs, the frequency equals constant F, okay, which this is in physics, that's your force constant, okay, and this is the mass of your balls connected by a spring, okay. This is frequency of vibration. Okay. This is your force constant. And you can think of this as the strength of the spring. Okay. And then this is the mass of the weights. Or ball, I guess I would say. Okay.
What is K?
K is another constant, which I'm blanking on right now. But in any case, what I'm trying to convey to you is when you change one variable in this, what is the effect you're going to see in terms of absorption of UV light. Okay? So I mean, we're not really worried about, we're not talking about weights on a spring, right? But since the vibration of a bond mirrors that, okay, we can use this to sort of think about, well, what kind of changes do we expect in vibration if the bond changes? Okay, so this is the strength of the spring, all right? In this case, it would be the strength of the bond, all right? And you can see that it is positively correlated with frequency. Okay, the stronger the bond, the stronger the bigger the frequency. Okay, the higher the frequency. And the lighter the weights are, the lighter the atoms are of the bond. Okay, so your denominator goes up, or goes down rather, so your frequency goes up. Okay? So the frequency increases the lighter the atoms are. Does that make sense? All right, perfect. So, with that in mind, let me give you just a really crude schematic of how an IR instrument works. Okay, so you have your sample chamber, okay, and some light source, okay, operating different frequency of the IR spectrum, okay, all right, and then you have a detector. And there's a lot of instruments in chemistry that work this way. We're actually going to use one next week, a spectrophotometer that operates off the same basic principle. Okay? And you can vary your wavelength within that IR spectrum, okay, that goes into the sample. And then if you have an idea of what type of bonds absorb, okay, at different frequencies, all right, you can see, well, if at that frequency the detector doesn't pick up the light that went into the sample, it was absorbed. And so you have an indication, a suggestion, in some cases, pretty good confirmation, but in other cases, a suggestion that you have that bond in that molecule. Okay? Does that make sense? All right. So let's talk about the different frequencies the different bonds come at. Okay, there's a couple funky things that that we do when we examine an IR spectrum, or when we create an IR spectrum. The first thing is that they wanted to sort of focus the scale on wavelengths, okay, rather than frequency. And it probably ends up with how the spectrum ends up spreading out. It spreads out nicer that way. However, they also wanted it to be, remember that energy of vibration and wavelength are inversely related, right? As the wavelength gets smaller, the energy gets higher, or as it gets bigger, the energy gets lower. Okay? They wanted to base it off wavelengths in a sense, but they wanted it to be directly related. Okay? So, very simple solution to that. We'll take wavelengths, all right, but we'll use the inverse. All right, we'll use 1 over the wavelength. Okay, and that is called a wave number. Okay, so rather than wavelength, it's wave number. Oh, of vibration. Okay? Hopefully you can still see this. Maybe ish. And the lighter the atoms, okay, also the higher the frequency. All right. So important functional group absorptions. Okay. So I don't know if I conveyed that well, but you know, if you have two particular types of atoms, okay, say a carbon and a carbon, okay, and they are connected by a double bond, all right, that vibration is pretty consistent. Okay, you're going to find that there might be a little bit of variation depending on the other things that are connected to those carbons, but it's pretty consistent about where it comes on the spectrum. Okay, and it's different from where a carbon-oxygen double bond would be. Okay, that's the whole basis of this. If it wasn't consistent, then this would be useless. All right. So where you see absorptions on the spectrum of some compound that you put in the instrument gives you an indication of what kind of bond you have. Okay. Oh yeah, so we use these wacky things called wave numbers. All right. The unit, okay, we know that the wavelength is going to be in some kind of meters, but this is not wavelength, this is wave number, which is the reciprocal, or unit's got to be reciprocal. So it's actually centimeters to the -1, so it's 1 over centimeters, also known as reciprocal centimeters. Right? A little bit wacky how this is set up. May seem a little bit strange, but my guess is if you tried to do this versus frequency, if you tried to do this versus wavelength, it wouldn't spread out the different absorptions as nicely, would be my guess. Oh, all right, so and the other wacky thing is rather than examine it by absorption, and you may remember this from Gen Chem, you can look at the absorption of light, okay? I should still have my box up here where it's going through the sample. Okay, you can describe it in terms of an absorption, okay? You can also describe it in terms of transmittance. How much of the light was transmitted? Is it 100% of the light was transmitted at that wavelength? Then that functional group's not there. Does that make sense? If you only get 20% transmittance at that particular wavelength, that means of the light that went in, only 20% came out. Okay, so so the y-axis on an IR spectrum is actually percent transmittance. Okay. All right, so some wacky stuff here. Reciprocal centimeters, percent transmittance, and then just to finish off the wackiness. We tend to describe these things when we're discussing an IR spectrum. We tend to say, oh, we have this absorption here, even though our x-axis or our y-axis is percent transmittance. We still discuss it in terms of absorption. All right, so let's see. Okay, hopefully I've made this wide enough. Okay, so that 3,500. 4,000. Okay, this is 30,000. All right. This may not be the scale. 2,000. What do I want to put here? I want to put 1,500. There's some interesting stuff that goes on here, so I'm going to add in 1,700. least on my picture here, I need a little bit more space, I think. Spread this out a bit. Think of that, 1,000. Yeah. It's 500. All right. And like I said, there's a bit of a range, right? You know, we're going to learn that alkenes are around 1,500, but it's not, you know, oh, they got to be 1,500 on the nose. It's going to be 1,500 plus or minus, okay? And within a given compound, you actually can see it won't be one specific wavelength or reciprocal wavelength where that double bond absorbs. Okay, it can actually be over a small range, so you'll see absorptions like this. Okay, now some of them will be very sharp. Okay, where no, it's really just that specific wavelength. Let's keep it simple and stop talking about wavelength. It's that specific wavelength that you get the absorption for this particular alkene in this particular molecule. Okay, and so it'll be sharp. Some of them tend to be more broad. Okay, if you have that functional group in that molecule, then there's a bit of a range where you see absorption. All right. Some of them tend to give you a lot of absorption. Okay, and so you'll see a spike that goes way down because your transmittance is going way down. And some of them give you a little bit of absorption. Okay, so we describe these peaks with these types of adjectives. Okay, we tend to say broad or sharp. Okay, and we tend to say strong for a good absorption that goes, you know, kind of all the way down. All right, or medium absorption, or even weak absorption. Okay. All right. So, in the first area, we have. Sorry. Okay, so we see sort of two basic critical types of absorptions in this, around 3,500. Okay? And that is OH bonds. Okay? It could be an OH bond of an alcohol, it could be an OH bond of a carboxylic acid. Carboxylic acids tend to be really broad. All OHs tend to be a little bit broad. That's why I drew it kind of lighter. All right, and a good range to learn for OHs is 3,200 to 3,600. And it tends to be broad and strong. Sort of right in the same area, and you'll either sometimes see it as, I don't know, like organic chemistry teacher years and years ago talked about teeth for this particular one. You'll either see it as one teeth or two teeth, okay? And that is an NH bond. And the NH, that's going to tend to be like, same kind of range, 3,300 to 3,500. Okay,